Good morning, good afternoon, and good evening, everyone. Thanks for joining us for another Data Engineers Lunch. This is going to be Data Engineers Lunch 97. We're getting closer to that 100 mark. If you do have any ideas for special events that we could do for our 100th episode, please reach out to me at acqui@anant.us. We're trying to put something special together for that 100th episode. We're really looking forward to it. But for this afternoon, we have a special presentation by a returning guest, Obi Anamnachi, and we're going to be going over Hadoop Distributed File Systems. The hosts for this event are Raul and myself. We are looking for speakers and sponsors for this event. If you're interested in any of these opportunities, please reach out to me at the email address listed below. We are a part of a larger community called Data Community DC, which believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome, and we expect respect to be given to all. Data Community DC is made up of a bunch of smaller organizations. You can find out more about these groups at the addresses listed below. So what do we cover here at our Data Engineers Lunch? If it's your first time joining us, we cover everything from the egress and ingress of data and everything in between. If it is your first time joining us, please go ahead and introduce yourself in the chat, maybe how you heard about our Data Engineers Lunch, where you're hoping to learn from our lunches, and group rules. If you have a question, go ahead and ask it. Obi does like his questions asked when there's a break in the presentation, so either a break in the slide, or let's say we're switching over to the demo. That'd be a great time to just go ahead and drop your questions in the chat. As I mentioned earlier, please be polite and courteous to others. And we do want this to be an inclusive environment, so we do want you to share what you know with us. Here at Anant, we design, build, and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. We'd like to thank our program sponsors, along with our organizational sponsors, for the continued support. We'll take a quick second for 15-second announcements. If you have any jobs, meetups, hackathons, conferences, or classes coming up, please go ahead and drop those in the chat, along with a quick description and a link. Our recurring events, our data wranglers, our data engineers lunch every Monday, as you know, our sister lunch, our Cassandra lunch on Thursdays at the same time, and our no code, low code event is on Wednesday afternoons at 1 p.m. Eastern. If you haven't already, please make sure you're subscribed to our YouTube channel so you're notified when we go live. Also, our meetup groups are a great place to meet other data professionals and get updates on our upcoming events. And then finally, this is a final call for our latest runbook, which is runbook 17. This runbook will be replaced this week. So if you haven't already, I'll be dropping a link to this runbook in the chat. Go ahead and download it. It is free while it's still available. But please make sure you get that before you leave our session here today. And with that, I'll go ahead and hand it over to our speaker for this afternoon, Obi. Obi, over to you.
All right, thanks, Akwi. Give me 1 second to set up my screen. All right, as you heard, my name is Obi Anamnachi. I'm an engineer here at Anant. Today's topic is HDFS and distributed file systems more generally. We're going to talk about Hadoop Distributed File System, which is HDFS. We're going to talk about using it together with Apache Spark, and we're going to talk more generally about distributed file system models. And we'll go into a demo where we not only use HDFS, but also use it alongside Spark. So first, HDFS is part of Hadoop. What is that? So Hadoop is a processing engine for distributed processing large data sets across a computer cluster. It's scalable, so single server instances to thousands of machines. Each machine has its own computation and storage. It runs on commodity hardware rather than needing like a supercomputer to run. It's high availability, so when nodes fail, it detects and handles those failures and is able to resume processing. And so the service itself is highly available on the cluster, regardless of the sort of health of those individual machines. It's made up of Hadoop Common, which is just basically the supporting infrastructure. HDFS, which is the topic of today's talk. It's a distributed file system where you can get high throughput access to your data, stored in file system format rather than in a database. Hadoop Yarn, which is a resource manager, a framework for job scheduling, resource management, and stuff like that. And then Hadoop MapReduce, which is the actual processing data that uses the MapReduce programming architecture, where you have a map step and a reduce step, and your data set runs through, it gets mapped, and then it gets reduced, and you get out your results. There are more advanced processing engines available these days, which, we're talking about Spark later. But first, HDFS. So just an overview: primary distributed storage for Hadoop applications. It's specifically a file system, not a distributed database. The architecture, the sort of cluster, is made up of a name node, one name node. Well, there's a secondary name node, but it's not running at the same time that the primary name node is running. And then many data nodes. So one name node, many data nodes. The name node manages the metadata for your files, and it's the center for control and coordination of the entire cluster. And the data nodes store the actual data. One interesting thing that we'll see about the difference between name nodes and data nodes is that the name node doesn't actually do anything by itself. It gets pinged by the client and by the data nodes. So to keep track of, say, whether data nodes are available, they ping the name node every so often, and it keeps track of that heartbeat. And if it hasn't received anything in a while, it can mark that data node is down and say, go to a different replica for that data. But there aren't any processes that are continually running on the name node, really. It has a web interface. The name node and data node run internal web servers. You can sort of access their pages to look at your file system, which personally I was not able to get working, but that might be a quirk of Gitpod rather than the actual pages being unavailable. But that's something we'll see during the demo. You can look at basic statistics about your data and your cluster, and then you can also access it with the Hadoop shell commands. So HDFS is their actual command line command. Then the subset of commands you're using is the DFS, distributed file system commands. And if you say -help, it will list you all of the commands that you can do. And they're both basically all of the things that you could normally do in a file system. So make directories, delete directories, move files, etc., alongside put and get, which are for placing and retrieving data from HDFS to begin with, alongside specific operations that you couldn't do in a normal Linux machine because they're specific to HDFS. Like you could change the replication factor for a specific piece of data, and other settings like that that are unique to data in HDFS or other distributed file systems that aren't necessarily there for regular file systems. So looking at the architecture of HDFS, so we talked a little bit about what, we talked a little bit about the structure, having one name node and multiple data nodes, and that the name node is the manager that manages file systems and access to data, whereas your data nodes manage the storage, and they handle read-write requests of your individual data blocks. I think that's actually the first time I mentioned blocks. So any file that you store in HDFS is split into blocks. These blocks are generally all the same size. They have a maximum size that's set by default at I think 128 megs or perhaps 64 megs. But regardless, there's some default value, and the standard block is going to be that size. So when you store a piece of data that is bigger than that size, it splits it up into blocks of exactly that size, and then one block that can be less. So if you put in a file that is less than the block size, it will create one block that is smaller than the limit. But if you put in a file that is, say, 2 full blocks and then a little extra, it will create those 2 full blocks at the data limit and then create one extra. And then the name node holds not only the metadata for the files, so the names, where the replicas are, things like the data size and other things like that, ownership data, that's all being stored in the name node. And you can still access it through, like if you use the ls command with the proper flags, it will still tell you the ownership information and stuff like that. And then the actual data that's split into blocks is getting stored on the file system in the data nodes. So this is contrasted to if you use DataStax Enterprise DSE, it has an analytics node, Spark, and that comes with DSEFS, DataStax Enterprise File System. And the thing about DataStax, or about DSEFS, is that it's actually backed by Cassandra, which is the main technology of DSE. And so all of your blocks are actually being stored in the database, and it's handling the replication and the retrieval and stuff like that. Whereas in HDFS, your blocks are actual files that are getting stored on the file system, just on the data nodes distributed across the cluster. And then when the client wants to read them, it basically gets the metadata from the name node, so that it will know where to go to get the data from the data nodes. So if there are block operations like replication and stuff like that going on, those are handled by the name node. So if you change the replication factor of one of your files, it will put new blocks in different nodes. And then, of course, this is all affected by Hadoop cluster topology. So replicas are generally split between racks as well as data nodes if you have them. And we'll take a look at that a little bit later. The name node executes namespace operations. So if you want to open a file, close a file, or rename it, really anything that changes the metadata is going to happen on the name node, and it determines block to data node mapping. So where your blocks go in terms of which data nodes they're actually sitting on. And then the data node needs to serve read and write requests from clients, handle block creation, deletion, and replication, and follow any instructions that are given into it by the name node. So looking more specifically at the replication, HDFS is generally determined for storing large files, small amounts of large files that get divided into blocks for efficient management. The blocks are replicated for redundancy. So if a particular data node is down, other data nodes can theoretically serve that request. You can configure your block size and your replication factor. And like I said, this interacts with your Hadoop cluster topology. So data nodes that are running inside the same rack, which is a sort of logical organization layer for your Hadoop cluster, they're going to prefer not to have replicas of the same data. So if you have enough racks available for the amount of replications that you pick, they'll all be put on different racks if possible. And then so blocks are variable length in that if there is enough data to make a block of the maximum size, it will do that. And then one final block, if that exists, will be of a different size. There are potential, there is potential functionality that can be added if you use append or something like that to make more variable length blocks. But ideally, if you're storing data into HDFS all at once, like you have a file and you're putting it into HDFS, it's going to be split into these blocks of all the same size and then one extra potentially. So if you would want to use HDFS and Spark together, how would you do that? So Spark itself was designed as a replacement for Hadoop MapReduce, or an extension of Hadoop MapReduce, which means that the processing engine in Hadoop, or the processing engine that is Spark, is meant to slot in where Hadoop MapReduce previously went. As such, it's compatible with a bunch of the other other Hadoop stuff. So specifically, you can use Yarn, which I mentioned earlier in the Hadoop section, as a resource manager for Spark. And it's also compatible with HDFS in the sense that when Spark wants to load in data or load in files specifically, it's nearly as easy to do that with HDFS as you would with just files that are on the normal file system on that node. So the way that you actually do that, though, is inside one of your Hadoop settings files, core site XML. There's a default FS setting, which determines basically the HTTP address. It's not actually an HTTP address, but the address that you use to access HDFS. And then if you append that to the file path within HDFS, you can pass files to Spark using the text file loader or the text file stream loader, just like you would if that file was on the normal file system. And then just generally, so distributed file systems come from this Google file system paper released in 2003. And you can see its architecture actually has a lot of similarities, has a single master and many workers. You see the GFS master here contains the file namespace. So it's taking care of all the metadata, just like in HDFS. And then the chunk servers store their data on the Linux file systems on those machines and communicate with the master in order to serve requests. Communicate with the client in order to serve requests, and the master in cases where you need to get metadata about the file as well. And you could contrast this with something like, if anyone remembers IPFS, Interplanetary File System, which was a big part of actually like Web3 infrastructure. If you made an NFT that was referring to a file, you would generally try and put that file in IPFS rather than putting on someone's actual server. And theoretically, that would be just as immutable a record of that file as data that could actually be stored on the blockchain itself. But the way that system works is it's a peer-to-peer system. So rather than having one master and a number of workers, it's fully distributed. Every node in the system is identical. And the way that it will work is it would assign your file a particular ID and put chunks of it. It would split it up into chunks, just like these distributed file systems do, and distribute them among your peers. And essentially, you would go and ask your peers if they had it. But the way that those requests were actually made performant was basically you would ask some number of people, and they would ask some number of people, and they would ask some number of people, and then you get your result back. So theoretically, you could scan the entire namespace for the particular ID you're looking for without going too far out of your way, or taking too long. But it avoids having this master worker architecture, but still theoretically manages to store your data in a distributed manner. So some advantages of this system over that system is because you have this master that's taking care of the file namespace and all the metadata, you can actually do operations like rename or append. Things like that wouldn't be possible in IPFS, which once you put something on there, it's immutable. So just the different potential ways that you could sort of replicate a file system, or at least, file storage, have different advantages and different disadvantages. All right, we're going to move on to the demo in a little bit. Any questions? This would be the time for them. And we can actually look at the Google file system paper and see when they talk about architecture, they're talking about a single master server and multiple chunk servers. And they actually talk about later on the performance of a number of clients trying to access data at the same time, and the way that more reads and writes and more clients actually reduce performance over time, not really approaching the network limit. And here you can see how append is an operation that's even less performant as you get more people. All right. So for the demo today, we're going to look at this. It's from this old 4-year-old Hadoop Docker image repo. This does not work if you just try and run it. So there were edits that made this run, and what I've done is that we'll look at in a little bit, is make it run Hadoop, so it's running HDFS, and then Spark on the same single node, and then we'll see how you can access files that are stored in HDFS in Spark and see those results. But first, let's look through actually, let me start building these because it needs to download both the Hadoop tar and the Spark tar to actually be able to run. So it's best to start that now. But if we look at the Docker file, so this is the base image. It's using actually a very old version of OpenJDK with stretch. And we actually have to go and download the list of stretch sources because a lot of them are not included in the current list of sources. And then we install all of the sort of prerequisites, SSH, which is required for Hadoop. And it's actually one of the reasons that Hadoop straight out doesn't work on Gitpod. So if you see, none of the ports are open on this machine by default. So one of the requirements for installing Hadoop is that you need to be able to SSH into the machine without a password. And so it just will not connect. So instead, what we do is we create this Docker container and we set up passwordless SSH by creating our key, putting it in authorized keys. And then we go get the Hadoop tar and unzip it. This time specifically, we're using Hadoop 3.3.6 and installing that on our machine and adding it to the path. So we'll see once we get into the container that we can use question. What happens when the name server becomes unavailable or is lost completely? So this is something that I touched on a little bit. But if you see this setting here, Hadoop secondary name node ops, essentially there is a secondary name server that it's running either as a process on the same machine or on a different machine that if the name server process fails can take over. So there is some redundancy, but if all of your secondary name servers are lost as well as your primary name server, then you would not be able to access and eat your data. What was I talking about? Okay, so the Docker file, it installs Hadoop, and then down here, it downloads the Spark tar and unzips that as well into the same directory. So the things we're doing, oh, and something I mentioned earlier, the core site XML default FS value. So it's HDFS localhost 9000, but you set this value, you can change it to basically whatever you would like. And then, so changes also had to be made in this Hadoop environment where we are setting all of these usernames manually. So because we're in Docker and we set up our passwordless SSH to be used with the user root, we need to make sure that all of the HDFS processes are also using that user. So that's the Docker file for the base Hadoop image. But what we actually use in the Docker Compose here is we're setting up an HDFS name node image called name node using this Docker file, which essentially just runs this script file that starts HDFS on the machine. So we bring up our Hadoop machine. You can see we have our two ports, port 9000 and port another. New to HA file system is expected that Goldmaster copies of the files live elsewhere in HDFS is used to make them highly available and for read throughput. So I can't say I've ever used HDFS in a production system, but it's highly resilient to data nodes expiring and even a single name node going down. But it's primarily used, yes, to make them available for high throughput reads into a processing engine. So theoretically, you could have your files live somewhere else, although Spark is also able to read from S3 and Google Storage and Azure Storage. So I don't know if that would necessarily be how you would want to do that in the modern day. But files in HDFS are able to be read very quickly into a Spark context for processing. And that's sort of the advantage here, that you could use them in MapReduce or use them in Spark to do analytics on them and be able to load them in very quickly. Okay. So we're going to attach to our Docker container. And we can see, okay. Zoom in a little bit. So we can see there is our Hadoop folder here, as well as our Spark binaries, both untarred inside this container. So the first thing we're going to do is show that HDFS is in fact on this machine. Currently, there is literally nothing in it. So the first thing we need to do is make a directory for our user. And remember that our user is root because of the settings in the Hadoop environment sh because of the settings in the Docker file. So now it's no longer non-existent, it's just empty. So what we're going to do is we're going to put some data in here. And we're going to use -put. And then we're going to tell it to use from the Spark examples. Streaming data set, afn111.txt. And now if we ls, we have our data in HDFS. And you see that you can use all the same flags for ls and get back the metadata, including date, ownership, size, all that stuff would be stored on the name node, while the actual content of the file would be split up and stored in the data nodes. I am not in the sheet. So now if we open the Spark shell, so for this, I originally wanted to use the Spark streaming example, but it is essentially looking in the wrong place for files. To begin with, the stream reader, when set to a directory, only pulls in new files from that directory, but it's has some issue with HDFS currently that I haven't been able to solve. So currently we'll just use the regular text file reading because we already put the file into HDFS in the Spark shell. Remember that when we want to query HDFS, we need to use this value here. So if you look at the read command, Spark context text file. So it loads a text file from the place that you tell it. So you can give it a location on the normal file system. See. And well, this isn't actually indication that it works because Spark uses lazy evaluation. So from the normal file system, we can see an error. What's this error? It's already looking in HDFS. Strange. So even the default, that should mean we should be able to access our file with just this normal file path without specifying the file system value. So I think because we set the default file system here to HDFS address, then we're actually looking there by default and not in the literal file system of the machine. But you can see we were able to load all this data, just like sentiment analysis or something, of these different words with scores into Spark, and we can do processing on that. It currently, if you use the text reader, it loads as an RDD, but you can process that into a data frame, do manipulations on it, and do any of the things that you can save a data frame. That is the end of the demo. So if there are more questions, now would be the time to ask them as well. There are parameters similar to RF that controls how many times data is duplicated over the nodes. Yes. So if we say HDFS, DFS, health, get a full listing of the potential commands. Maybe it will be best to do this in a single. Here we go. Okay, so all of the commands that we're looking at. No, set rep. Okay, here set rep, set the replication factor of a file. If path is a directory, then the command recursively change the replication factor of all the files under the directory tree. So you can set this for any particular file or directory inside HDFS, and you can specify that it's your wait, or you can let Hadoop do it on its own time. But essentially, this triggers more replicas to be created if you would like to do that. So you can set this replication factor generally for, say, your top level directory, and all your files that are created will be created with this replication factor, or you can set the replication factor for individual files inside of your directory.
All right, I think that may be it for any questions. If you have any questions, just go ahead and put them in the chat as we close out. I want to thank Obi again for another fantastic launch. I want to thank everybody for joining us again this afternoon and starting off your Monday with us, and everybody who may be listening to this a little bit later or watching this a little bit later. Cool, and just some thanks in the chat for you, Obi. I want to thank everybody for joining us. Again, just a few housekeeping items. We will be back again next week. I'll kick off our series. We're really excited for that. Alex Mercer will be returning. Also, our our sister launch, our Cassandra launch, is this Thursday at the same time, and our no code, low code this Wednesday afternoon at 1 o'clock Eastern time. Again, thank you so much, everyone, for starting your week with us. We hope you'll be able to join us throughout the rest of the week and next week as well. Take care, everybody. We'll talk to you soon.